I determined whether the three given side lengths can form a triangle. If not, explain why it doesn't work. So let's look at A. So the two short sides we need to acknowledge are 5.1 and 3.24 inches. So when we add those, 5.1 plus 3.24, then I get 8.34. Now 8.34 is more, it's more than the 8.25, so could we make a triangle out of this? Yes.
Oh.
Find out. So 4.5 is the same as 4.5. And 3 3/4 is the same as 3.75. So these are the two small sides that I need to add. 4.5 plus 3.75. Now this number that I get needs to be more than 8. I got 5, 12, carry the 1. I got 8.25, which is bigger than this 8. So this one also is a yes.
Oh, yeah.
Well, let's try C then. On C, this one is 5.25. That may be easier or harder, I don't know. But in any case, the two short sides are the 6.01 and the 5.25. So let's add those. 6.01 plus 5.25. And I got 11.26, which is bigger than this one. So this one also, could we make a triangle? Yes. Yeah, so D we would kind of expect to be no, just based off of some basic experience. But again, this is 4.5,
But it said jet, no.
3.25. So I need to add these, 4.5 and 3.25. And this number needs to be more than 8, right? Well, we get 7.75, which is kind of close, but yep, this one is a big no.
I got 8 point.
Number 2, your friend is having a hard time understanding how angle measures of 30, 60, and 90 might create more than one triangle. Draw two different triangles that have those angle measures and explain why the two triangles are different. Alright, so to do this one, we only need to first we need to draw the 90-degree angle right here. Now in order to make this 30, 60, 90, then this one may be the 60-degree angle. Just put it on my desk, please. And then this one is 30 degrees right here. Alright, now that would be one triangle with those three angles. But well, not necessarily. So we know those add up to 180. But what it wants to know is why can we make more than one triangle with this? Because I can make the sides longer and still have the same angles. So this one would still be 30 right here. This one would still be 60 degrees. But see how it's much bigger? And we still got that 90-degree angle? So with the same three ankle measures, I got two very, very different sized triangles, which is why we can have these three angles and have more than one triangle. Your friend is having a hard time understanding why knowing the lengths of two sides of a triangle and the measure of an angle not between the two sides, which means it's not included, may not be adequate information to construct a unique triangle. What that means is we could create more than one triangle. Draw an example where two sides of a non-included angle give two different triangles. So on these, I just need a length on this first. Now the length of this isn't really important. We could say that it is and just say that this has a length of 5, just because, right? Now, if we have an angle that is not included for another side, so to make this other side though, I'm going to have to use a circle. Alright, now you guys may be wondering why I have a circle here. It's because I have a circle because the distance from the center to any of the edges is the same distance. So, in other words, because it said the angle is not included. That's a radius. So I could have this length right here, or this one right here, and they're the same length. But I'm using the same side length, right? So I'm really looking at the ankles. But I'm using the circle to show that I can have two side lengths. So if I had a set non included ankle, the non-included ankle would have to be on the other side of the 5 length over here. So let's say that we had a smaller side ankle somewhere over here. Now I've made this line especially long for a specific purpose. Let's get rid of this garbage. Okay. But it's to show mostly that this ankle between the 5 and the side length that I just made is the same. So this ankle is set. Do we know the degrees? No, we don't have to though. I mean, we could say that it's 20 degrees and call it good. All right, but it's not included with those other side lengths. So the other side lengths, right? Let's make one triangle out of this and we'll show why we can make 2 out of it. All right. So I'm going to start from the center and come up right here. That didn't quite work. That didn't work out very well. Let me try again. So you guys see that I've got a triangle right there, right?
Yeah.
And I've got the length. The length right here is set. So we could say that this length right here is 1. That's the radius of that circle, right?
Yeah.
But I could also make it so that it goes to this point, which also has the same radius. This one right here. So I'll connect those as well. And you see now how I've got 2 triangles right there? Let me highlight them, right? So I've got this triangle right here.
I see it.
But then I've also got this triangle in green right here. Now this length is still 1 though. So I've got a non-included angle that gives me, as it turns out, 2 different triangles, which means it's not unique. I can make more than 1 triangle given 2 set side lengths and a non-included angle. Let me try again on this. So if I go up in here, let me make my non-included angle first. Alright. Alright, so keep in mind that cycle right there, alright, because that's what that rotation stuff is about. Alright. So I'm going to make essentially kind of the same triangle in all of these. But I want a fixed ankle up in a here. So what is that? Something like this. So on this one, let's start with the ankle.
Like I like this class.
Right here.
Rotating.
Now, I'm going to see if I can rotate this stinking thing. But I'm going to rotate this a little bit differently. So you see that angle. We can't change that angle, but it's not included. So it's not included for this side, which we'll say is, let's say is J. We'll call this side J. But then I need to make another side, I don't know, K. Alright, and this side length has a length of K. Right here. Alright, now it's important to remember that this long side, right here, this is not a set distance, which means it could be shorter, it could be longer if we need it to be. In this case, we're going to make it shorter so that we get the same length K, but I'm going to have it connect probably somewhere over here, okay, which is going to give us a separate triangle. Yes! I know, I haven't got it rotating yet. But this is one triangle, alright, so keep track, we got this big one, but again, I got that side, which I can make shorter, right here. See how that gave me a shorter distance for that other side length? But I still got my value K right there, right? That's one triangle. This one, I mean, we could say it's bigger, not this. This one is bigger. It's one triangle, but then I can get a separate triangle right there. That's a smaller triangle. Bam. Now it's rotating. Watch, it's going to come back. It's going to touch the point right here. 1. And it's going to come over here and it's going to touch
2.
right here. There it is. See, it gave us 2 triangles right there?
Yep.
So number 1 right here, draw and label triangle ABC with lengths AB5, length BC7, and length of CA10. Alright, so it doesn't have to be any specific triangles, but we should know if we have a length of 5 right here. And if this one is 7,
It should be longer. What are you
then this length would be something like 10 right here. Well, no, because we need to label these now from A to B was 5. From B to C was 7. And then it told us AC was 10.
Oh.
Now, would this be an obtuse triangle? We don't know right now, and we don't really care, but eventually we will know. But we could certainly make a triangle out of these values. So draw and label triangle ABC with measure CAB of 40 degrees, BCA 50 degrees, and measure of ABC 90 degrees. So the vertex B is going to be where the 90-degree angle is. Where A is will be the 40 degree. So I'll do something like this. Well, something like this.
Why is it
So I would
right
say this one is 40 degrees. And then I'll just finish this one off at 50 degrees. Now we know that this is A because A is the center letter radical. And we know that this is C because this is the center letter radical. So that's where the 50-degree angle has to be. Now once we start using protractors, we'll be a little bit more proficient at this. But for right now, we just need to be able to envision this stuff. Like number 3, draw and label triangle ABC with measure CAB of 60 degrees. So let's do that right now. 60 degrees would be something like this.
Cute, something like
So it is acute, certainly. But we can at least label these, right? CAB. Now CA, it says, is 4 units. So BA is 6, which is a little bit longer right here. But then we'll just connect this one. We don't have to know that other length yet. Eventually we will, but right now we don't. So that'd be fine. Yeah, very good. So on A right here, the 2 plus 5.
that. Equals 7, but you told me that it doesn't have to equal, it has to be like bigger than
That's right. It can't be equal.
that. So it's no.
So this one is a no. So what about this one? So we got 33 and 70,
It's a yes.
which would add up to 103, right? Which is more than this 93.2, so yes.
And then would you add 1
Yes.
and 2 and 7 together?
So this is 1 and 2.7,
1.
Oh.
which is 3.7, which is not as big as 7. So this one is a no as well.
No?
Determine if the given information will make a unique triangle. Explain why or why not. Side lengths 3, 5, and an included angle of 67 degrees.
It wouldn't.
So this one would, because if I have a 3 and a 5 at 67 degrees radical, then I can't change the angles to make this other length bigger. So as it turns out, I can only make one triangle with this. So does it make a unique triangle? Yes.
How about B?
Whenever we have 3 angles, we can always change the side lengths but have the same angles. We already looked at one like that. So this one is no, you could not make one unique triangle.
And then
What about angles of 80 degrees, 25 degrees, and included side of 12? So let's look at about what that would look like. So if this was 12, I'd have 80 degrees, let's say 80 degrees right here. And then the other angle would be 25 degrees, something like this.
No.
So I can only make one triangle out of this because we have these 2 angles are fixed. We can't move them, so we can't change the length or where this point will intersect right there. So this one, could we make a unique triangle? Yes. All right, 7, we need to determine if these will make a triangle. Do you guys remember what we need for the angles to make a triangle?
More. And that one's the same.
Well, for angles, as it turns out, we just need them to add up to exactly 180 degrees. So this one is 25
25
plus 70
plus 70
plus 95. Now we need it to equal 180, but as it turns out, this one looks like it would be 190.
No, too much.
Yep, too big.
10.
So this one would not make a triangle.
Do the no.
What about this last one? We got 30 plus 40 plus
It'll be
20.
90 degrees, I think.
So yeah, this one is 90 degrees, but again, it needs to be 180 degrees.
Yeah, so it
So
needs
this one
90
is also, yeah, it would need 90 degrees more. Very good. I don't know why I put degrees on the no, but whatever.
Really get 6.
Let's do this one, then we'll go back. Below is a table that describes the dimensions, perimeter, area, and change of side lengths for a rectangle that's scaled in different ways. And we talked about this last time, right? If we double the side lengths, then we can double the perimeter, but we would quadruple the area, for example. In the first row, you'll find that the 5 by 20 rectangle has a perimeter of 50, area of 100. There is no change in the side length because it's the original. In the next row, we're going to compare the 10 by 40 to the 5 by 20, and we get the perimeter of 100 and an area of 40. The side length changes twice the original. Examine the other rows to understand what's happening to the rectangle, then graph the relationship between the perimeter and area on the graph below. Describe the patterns you notice. So very generously, they gave you guys the graph on these and scaled it and labeled them. So we're just looking at the perimeter. When I got a perimeter of 50, I got an area of 100. That's my original shape. 50, 100 would be right about right here. So that's this point, and I would label it 50, 100. Next up, I got 100, 400. So that's 100 right here, 400 right here, and that gives me this point right here, 100, 400.
Like 50, 100.
All right, next up, 25, 25. So 25 would be right about here, and then the other 25 would be right about right here. So this point is 25,
100.
25. So that was this point. Next up, we got 150 and 90. So I got 150 though, so 200, 400, 600, 8, and then halfway between that would be 900. So this one, 150, 900. Next up, we got 16.67 and 11.11. So that's where this point is right here. And then the last one is 200 and 1600.
Yeah.
200 and 1600 is towards the top up here,
Yeah, it's the second.
right there. So 200 and 1600.
And then that's all you have to do.
Well, no, it wants us to just acknowledge what's happening right here. We can see that this is kind of a curved line on these.
But why do you put
So if you had 0
400?
perimeter, you'd have 0 area, but would move this line upwards like these. So continuing at these,
Over there it says 100.
which means it's just going to get higher and higher. The higher the perimeter, the more the area will get bigger and bigger. But the perimeter, I'm sorry, the area is increasing faster than the perimeter is. So this is what we would consider an exponential
25, 25.
type curve,
Don't be 25, 25.
because the area is found by taking whatever we multiplied by and multiplying it by itself. So it's kind of like an x squared.